Welcome to the fourth week of our course, dedicated to potentially the most significant result in the field of quantum computing. I'm talking about Peter Shor's algorithm for function period finding. Why this result is so important? Well, because it allows us to factor big composite numbers, and as you probably know, for the classical computations, this problem is believed to be hard. Suppose that we have two big primes, P and Q, P not equals to Q, and we have calculated the product, which we call N big. Now all these tasks, finding big primes and multiplication, are feasible for classical computations. And suppose that these primes are 10,000 digits each, approximately. So this n would be like 20,000 digits. And now you have lost this P and Q, but you still have n. So the task is to find P and Q. And since n is a finite number and any number has only one set of primes, of factors, we can do this by brute force search from 2 to square root of n, since at least one of the factors, actually one of the factors, has to be less than this square root. And we can just take any number from this interval, from 2 to square root of n, try to divide n by this number and see if we have the remainder. And if we don't, we succeed, we find both factors. Now the problem is that for this size of P and Q, like 10,000 digits, we can do this search quickly enough. Honestly, we can do it, we can perform it in a universe's lifetime, assuming the reasonable growth of our computing power. Okay, brute force doesn't work here, maybe something else does. Well, maybe, but to our current knowledge, there is no classical algorithm that can perform significantly better than this brute force search. Behold, in this number, rather small, only 20,000 digits, we can store it in a file like 20 kilobytes, assuming 1 byte per digit. In this number, there is information about P and Q, but we can never retrieve it. Isn't that amazing? I mean, if you find two big primes and you calculate their product, and you publish this product, you will still be the only person in the universe who knows the original factors. And these factors can stay your secret as long as you want it. Now, this secret-keeping business reminds me of encryption. And yes, there are encryption algorithms based on this asymmetry of multiplication and factoring. And these algorithms are themselves asymmetric, which means they use different keys for encrypting and decrypting data, which allows you to do many things, like allowing anyone to send you encrypted messages only you would be able to read, or digitally signing some data, etc. The most famous such algorithm, RSA, makes possible handshake, the initial stage of the HTTPS secure connections on the internet. Now, this algorithm, the RSA, was invented in 1973 by English scientist Clifford Cocks. And this result was marked as classified by British government, which made it possible in 1977 for three American computer scientists, Ron Rivest, Adi Shamir, and Leonard Adleman, to reinvent the algorithm. So the algorithm was named by the first letters of their names, the RSA. And it is probably the most well-known and widely used algorithm nowadays. And it is believed to be secure as long as the factoring problem is believed to be hard. Now you can understand the importance of Shor's result. Because with Shor's algorithm, the factoring problem is not hard at all. And all the data which is encrypted by RSA right now, and all the protocols which use it, are insecure for big enough quantum computer. Well, here is the plan of this week's lectures. First, the introduction. You are finishing it right now. Then we are going to recall the RSA algorithm with idea and some examples. Then I'm going to explain how factor and period finding are connected. So how can we solve the factoring task if we can solve the period finding task. Then I'm going to introduce the new quantum operator, the quantum Fourier transform, QFT. And only then we can proceed to the algorithm itself, and this will occupy us for 2 lectures. So let's start.